What's going on, everyone? Welcome back to episode 4 of our Parser from Scratch series. Today, what we're going to be doing is we're going to be fixing a little bug which was introduced in the last episode, and then we're going to be working on assignment, grouping, prefix, expressions, as well as parsing types. So without further ado, let's just dive on in. And first, let's create a little test file for today's episode. So I'm going to come in here to 04.lang. And so I'm just going to basically replicate the stuff we had in here. And I'm also going to make sure that we have something like this. Plus 45 minus 10. 45 over 10 plus 5. There we go. So this is going to encompass our grouping. Let's also just add in a negative sign here for our unary. And let's, instead of making this plus, let's make this minus -5, like so. Perfect. So this is what we will be able to parse by the end of this. And then let's also just do foo equals bar plus 10 and foo plus equals bar plus 10. Yeah, let's say we want to do this. Is foo equals foo plus 10 and foo plus equals 10. These should both be equivalent statements. So these are assignment expressions. This is going to be what we call a grouping. This is a unary. And then at the end of the episode, we'll modify our let expression to support some sort of type, like let's say number, right? But for now, let's just continue on with this. So here's our examples. Let's go into the main.go, change the example to be 04.lang. And let's just run this just to make sure. Go run source / main.go. And we get nud handler expected for token dash. And if we recall, dash is this token right here. So let's go into the parser, go over to the AST first, go to expressions.go, and let's create a new type of expression. We're going to be calling this a pre-expression, which is a structure, and it's basically going to contain two things. The operator, which is a token, like so, and it's going to contain the right hand expression, or what we can call the right expr. And this is just an expression like so. So I'm just going to copy this function, come in here, and make this a prefix. There we go. So this is the type we're going to do for this. While we're at it, let's also go ahead and copy this. And let's create our assignment expression. Now the assignment expression is a little bit different. The way that works is we're going to have the assignee, which is an expression itself. And we're going to have the operator, which is a token. And we're going to have the right hand side, or RHS is what I'm just going to call it. RHS value, which is an expression like so. And I'm just going to actually call it value. I kind of like that better. There we go. And this is an assignment expression like so. So an assignee, obviously, here's two examples, right? We could have 10 plus equals 10, or not, sorry, not 10. A equals a plus 5. We could have a plus equals 5, where both of these cases, the assignee is a symbol expression, but we could have something like this too, right? Foo.bar plus equals 10, right? Where the left-hand side in itself is a member expression. So this is why it has to be an expression, not just a string. Okay, so now that we have this AST type done, let's minimize this real quick. And this, and this, and this. Let's go into the parser, and let's go into the lookups, and let's handle our bugs that we implemented in the last episode. So there's two bugs. First thing first, we don't need to actually be setting the binding power here. All nuds don't need to worry about precedence because they don't bind to anything to the left. So we can remove this, as well as in the BPLU, just completely remove that. So this should be the new nud function, which means everywhere we use nud, we just need to modify these so that way they don't have the primary, like so. So that'll fix that, and that'll actually prevent a few bugs from occurring later on in future episodes. Next up, what we want to do is when we parse the expressions, which is inside of the exper.go, when we parse expressions, there is a little bug. Currently, we're just letting the binding power get propagated all the way through subsequent calls. However, this is not what we want to do. Instead, what we want to do is we want to do the BP lookup of the p.current token kinds. And this is the binding power we want to be passing through. This will then verify that if the binding power, again, because currently we're just going to continuously say BP greater than BP, it's always going to be true. So it's going to keep propagating to the right. This will actually prevent that. So these are the two bugs that we needed to fix. And now that we have those done, let's go ahead and implement the unary / prefix expression. So if we look back at the error, it says a nud handler. And again, we can see why it's a nud handler is because there's nothing expected to the left of this minus sign, right? So let's just come in here and let's just do nud, and let's do lexer dot dash. And the function for this is going to be called parse unary parse prefix exper, like so. And while we're at it, let's also go ahead and create our assignments handlers, right? Now, what does an assignment look like? Well, if we look at this, we see that there's a left, the assignment operator, right? And then a right-hand side. So this means it's a led or left denoted, right? Here it's nud because it's not expected to be something in front of this. For example, this is a valid statement, right? Therefore, clearly this is a nud. However, this, an assignment has to have something to the left. So that's what's expected. So what we're going to do is we're going to do led. We're going to do lexer dot assignment, and we're going to call parse assign expression, like so. Now, if we look at this, plus equals is also a valid assignment expression. So let's do that as well. Led lexer dot plus equals, and this is going to be also parse assignment expression. And I'm going to copy this. I think we only support minus and plus equals, if I'm not mistaken. There we go. However, add star equals, slash equals, and modulus equals. This I want you to do for your language if you want. So let's now go ahead and create this function, parse assignments and parse prefix. So I'm just going to copy the name of this, go into the expression.go, and underneath parse exper and parse primary and parse binary, we're just going to create a new function called parse assignments. It's going to take in a pointer to the parser, the left, which is an ast.exper, and the binding power, which we want to parse. And if I'm not mistaken, I'm missing the binding power here, right? So we're supposed to pass in the binding power as the second argument. Oh my gosh, sorry about that. And the binding power here is assignment for all three of these, as we would expect. Assignment has the lowest binding power as well. But yeah, there we go. So now let's go ahead and create this. BP is a binding power, and it returns an ast.exper. Perfect. So now we look in the lookups, and that looks good. Let's then create the parse prefix function before we forget. So we're just going to do func parse prefix expression. It takes in a pointer to the parser and returns an ast.exper, like so. So let's just quickly handle the parse prefix, since this one's pretty easy. Currently, for us to hit the parse prefix, that means our current token is the operator. So let's just do operator token is p.advance, like so. And there we go. So now we have the operator token. Next, what we want to do is we want to do the RHS := parse exper, where we want to pass in the parser and a parser of defaults, like so. And there we go. That's basically all we had to do. Now we have the right-hand side and the token, so we can just return a prefix expression where the operator is the operator token and the value is the RHS, like so. Is it not called value? We called it right exper. That's fine. We can do that. There we go. So this is parsing prefix expressions done. And just to prove it, let's comment everything underneath this and make sure this all works. Why is commenting not working? That's weird. That is very weird. Missing return, expert godless 78. Yes, of course it is. For now, let's just do return assignment expression with nothing in it. And we can run this. And look at that. So we get a variable declaration where foo is equal to a prefix where the operator is minus, right-hand side is 45. So that handles that. Let's now handle the assignments expressions right here. So let's run this and see what we get. And we get an infinite loop because we're not doing anything, right? We're just returning nothing. So this isn't actually doing anything. So what we want to do is the left-hand side, in this case, when we're parsing an assignment, is already been parsed by now. So foo.var, whatever it is, has already been parsed on the side. So we need to get the token that we're currently at. So let's just come into here. There we go. And let's do operator token is p dot advance, like so. Then what we want to do is we want to do the RHS is parse expr, and we're going to pass in the parser, like so. And we're going to pass in a binding power of assignments, like so. Which means we could just also repeat BP. And then now, all we have to do is we just say the operator is the operator token. The value is the RHS, and the lefts, or the assignee as it's called, is the lefts. Now, why are we calling the assignee the left? If we look at this, right, when we hit the plus token, what's going to happen is this has already been parsed, meaning the current token is the equals. Then we parse the right-hand side, etc. So the left is that assignee right there. Let's now run this. And there we go. So we can see we have an expression statement where it's an assignment, foo equals plus equals 10. Here we also have one where it says assignment foo equals foo plus 10, right? So that looks perfect. Lastly, what we're going to do in terms of expressions is handle grouping operators. So let's run this and make sure we get an error. And sure enough, we get nut handler expected for open paren. So let's head into the lookups and define a nut handler for our grouping. So we're going to do nud, we're going to do lexer dot open paren. We're going to do parse grouping expr, like so. There we go. So let's go and create this function inside of here. So we're going to do func grouping expression, takes in a pointer to the parser. Since it is a led, it only returns an ast.expr, like so. And all we're going to do is we are going to do p.advance, which is going to advance past start. Then we're going to do expr := parse expr. We're going to pass in the parser and a default binding power. Then we're going to do p.expect, and we're going to expect a lexer dot close paren. And then we're just going to do return expr, like so. So this is a pretty simple function. Now we have grouping. When we encounter a grouping operator, we advance past the start, parse the inside, giving it a default binding power, which kind of just resets the binding power, and then we expect a close paren. Let's test it. And let's take a quick look. Let me also remove a few of these lines that we know work. And come in here, and let's just take a quick look at this. Okay, so we see that we have foo bar equals foo times 10. So we can see bar is equal to the left is foo times 10. And all of this is being added with a right-hand side of 45 over 10 minus -5. So we get left 45 over 10 quantity, right? This whole quantity is then minus a prefix of -5. So that looks like it's perfectly handling our precedence. So now what we want to do is we want to be able to have types. So our language is going to have types. For example, we want to be able to say const foo is a number, and then give it a value of 10, for example. Or let's bar :string, and then do bar equals hello world, right? So for us to support this, we're going to also want to have complex types later on. For example, things like arrays or array of arrays or of array of arrays, etc. We'll want to be able to have types like functions. So you'll be able to say something like function takes in a number and a string and returns a foo, right? So for us to be able to handle these types, we want to have a parser specifically for the types. Now don't get scared, it's not very complicated at all. So let's just get it. So by the end of today's episode, we'll actually be able to parse these right here. So if you don't give any type, it'll be defined implicitly. And if you do give a type, like for example, here you say const foo is a number, it supports both variants of the syntax. So let's go out of the expression and let's also create a new file inside of the parser called types.go, and this is going to be of type package parser. Inside of the AST, we're also going to go ahead and create a types.go, and so this is package AST. And let's go into the AST.go right here, copy this, and currently we have statements, expressions, and now type, like so. And so we're just going to make this underscore, like so. Cool, so let's go ahead and create our first two types. So we're going to do type symbol is a struct. It just has a name, which is a string. Right, so an example of a symbol type is t, or number, or int. You get the idea. There we go. So it's going to have a function. T is going to be a symbol type, and we're just going to call it underscore type. And the only reason we're doing this is that way this satisfies our requirement for a type interface, right? Then I'm going to copy this, and we're going to create a array type, right? Which is literally just a array syntax like this of t. Now, what does this mean? It means if we find this, we then expect another type, because we could have an array of t, or an array of t. You get the idea. So what this is the underlying, and this is a type itself. So this is a recursive definition. So we're going to have array type like so. There we go. And for now, these will be the only types we deal with. In the future, we'll have a function type and possibly pointer type or reference type. So now that we're done with the AST definitions, let's go into, let's minimize this. Let's go into the parser and define our types.go. Now, what are we going to do for this? Well, currently, the way we handle our types is in this lookups, right? We have a statement handler, nut handler, let handler, etc. But there's a problem with that. Currently, there's going to be overlap. For example, there's many ways in this language where you can use this syntax, right? Here's three different variants. The first one is array access, right? Array at index, something like this, right? This is what we call a computed expression. It's computed because this value may or may not be known at compile time. For example, you may have rands ints, right? Something like this is an expression inside of that, so it's computed. The other type of syntax you may have is you may have const foo equals 10 to 3, right? This is what we would call a array slash slice literal, right? This is another usage of the bracket syntax. This is what we would call a led, and this is a nud, right? However, notice how if we want to use another syntax with this, we kind of can't without cheating. So what we're going to do is say we want to do this, let foo : array of number, right? Well, this is a nud clearly, but how would we deal with this if this is going to conflict with this nud? So this is going to be a type nud, like so. So what we're going to do is we're going to create a brand new type system. Basically, all of these things we're going to copy and create a type variant of them. So I'm going to close that out of there, and we're going to go to the types.go. We're going to copy all of this stuff that we have right here. And then basically everywhere that we see, we're just going to add the word type in front of this. Like so. Okay, so this is defining our types. We don't need a statement. There's no such thing as types that are statements. So we can remove these two and this right there. Cool, which means we can also remove this. And then what we want to do is we want to do type nud, type led, type BP, etc. And then we want to have nud handler. Well, this is going to be a type nud handler, type led handler, and type binding power, like so. Binding power is just going to be the same no matter what, right? Okay, so let's just make sure this looks good. The led function here should be a type led handler, perfect. Led lookup, perfect. Nud, everything here looks good, except the type led handler should be an AST.type. This should return an AST.type, and this should return an AST.type instead of expression. So after all of that, that looks really good. So now what we're going to do is we're going to create a function called create token lookups. And I'm just going to call this create token type lookups. So just like we did in our lookups, we're going to define all of our types like this. And then we're going to call this function inside of the parser, inside of our create parser. So we're just going to call create type lookups like so. Okay, so let's actually go on this function and define how it's going to work. So what we're going to do is, what I want to do is first let's define the symbol type, and then we'll define the list type. So let's create a function, which is going to be called, let's just call it parse symbol type. And this is going to take in a pointer to the parser and return an AST.type. And all we're going to do is just do return a symbol type where the name is p.expect lexer.identifier.value. Like so. So this makes sense, right? If we hit a symbol, for example, something like this would be a symbol type. All we expect is an identifier, right? So that's all we have to do. Parse symbol type is done. Let's now put this in here as a nud. So we're going to do, type nud. And this is lexer.identifier, and then parse symbol type like so. Type nud. Let's make sure I defines type nud correctly. Type nud takes in a pointer to a parser. Perfect. And it returns an AST type. That looks good. Type nud handler takes in a token kind. That looks good. What else? What am I missing here? Let's see. Type nud takes in. It does not take in a nud handler. It takes in a type nud handler. And type nud lookup takes in. I'm seeing all the issues now. There we go. And then this is also a type led handler, like so. There we go. That makes a lot more sense. So there we go. So now we should have the ability to parse types like this. Let's create our type nud for lexer. What would it be called? Lexer.open curly bracket, right? And this is going to be a parse array type. And I'm just going to copy this function because I'm kind of lazy. And this is going to be parse array type, like so. So if we encounter something like this, for example, an array of numbers, if we encounter the open bracket, we then parse the right-hand side. And again, this will be another type, so we'll do that. So what we're going to do is we're going to return an array type where the underlying is the underlying type. And what is the underlying type? Var underlying type equals, and we're going to call a function called parse type, which we have not created yet. So don't worry about this. We will create it right now. Now, what is this parse type? Well, similarly to how we call a parse expression right here, and it returns an expression, we're going to be doing the exact same thing using our type parser. Now you could create a function which makes this somewhat generic, so it could be an AST_expr or a type. However, I am not going to do that just to make sure that it doesn't get too complicated. So I'm just going to copy this function, parse_expr, and change it to be parse type. And then it's going to return an AST type, like so. We're going to do a type nud lookup, like so, which means this should be a type nud. I'm just going to change this to say type nud and type led. And then here, we're also going to change this to be a type led lookup, like so. And everything else is identical. So that means right here, we can call parse type, get the underlying type, and then just put it into this underlying. So this is the entirety of our typed system for now. Currently, we don't have any led stuff. An example of how you would parse led stuff like this, though, could be number array. This is an example of a led syntax. And just to show that this works, after we get this working, if you want, we can just get this working. And then at the end of this episode, I'll just quickly switch it so we can show you how you'd parse a syntax like this instead of this. So for now, though, let's actually make sure that this works. And what we'll run into is we're getting an error about the let declaration, right? Expected assignment, but received colon instead. And that is because inside of our statements.go, we have our parse statement. We then have parse variable declaration. And what we do is we expect an assignment, right? But we receive a colon instead. So let's take a quick look at how we're going to alleviate that, right? So inside of here, what we want to do is we want to keep track of the explicit type. So let's change the variable declaration. In here, we have our explicit type. Let's just add this back in. So now we can come back here and we want to do explicit type is explicit type, like so. And I'm going to create a variable called explicit type, lowercase e. I don't know why it's doing that. And this is a type, or ast.type to be specific. And this is also lowercase e. There we go. So what we want to do is we want to check whether it's constant. We're already doing that. We get the variable name. Perfect. We then do not need to expect an assignment because there's two cases, right? There could be a explicit presence. And what we're going to do is we're going to check if p.currentTokenKind is equal to p.lexer.colon. If it is, then what we're going to do is we're going to do p.advance. And then what we're going to do is we're going to get the explicit type. So we're going to say explicit type equals parse type, like so. We're going to pass in the parser default binding power, like so. That's perfect. Then after this time, then we can eat the assignment operator, right? So if the current type is colon, we're going to parse the type, eat the colon, and then eventually we'll eat the assignment, right? And then, yeah. So now what we want to do is we actually want to handle the default case. For example, if we look in the code, this is a valid syntax, so is this, but what if I just want to do let foo colon number, right? So this has no default value for foo, right? So this is an example where we don't want to actually parse the assignment side of this. So what we're going to end up doing is, sorry, I didn't mean to open that. What we're going to end up doing is we're going to check whether we are at the assignment or not. Right, so what I want to do is if if p.currentTokenKind is not equal to lexer.semicolon, then we're going to do this part right here. And that means assigned value should also probably be defined up top. So we're going to do var assigned value is a expression like so. Cool. So if we are not at a semicolon, right, we want to parse the assigned value. If we are, if the explicit type is, what is that? It's equal to nil, then we want to do a panic, right? So we want to panic, missing either, right hand side in a var declaration or type. There we go, right? So here's an example of where this would fail. If we just did this, const foo or let foo, etc., this is not allowed at all whatsoever. You have to either give it a value like this, or you have to give it something like this. And with constants, even this is not allowed, right? So with constants, we have to give a value. So let's go back into the statement go, right? And this is the case that just makes sure that we'd assign a value if no explicit type is given. Yeah, now what we want to do is we want to make sure that that constant case actually works, right? This should not be allowed. Not allowed, right? Like this. So let's go ahead and let's check if is constant and the, assigned value is equal to nil, right? So if we have said we're constant and we have not gived a value, then we need to also panic with an error. So we're just going to do panic. Cannot define constants without providing value. Perfect. And then what we're going to do is we are going to do a lexer dot expect of semicolon, like so. And then we can just return our variable declaration. Now, let's quickly run through this, right? So we define our explicit and assigned values. Both of these could be nil, just not at the same time. If we're constant, we pull that out. We get the variable name. We then check if there's a colon. If there is, it's because it is a syntax like this, where we need to have a variable type. So we parse the type out of this right here. If the current token is not a semicolon, meaning we do allow this, right? But if it is not a semicolon, then we expect an assignment to happen, right? So we expect an assignment. And then if it is not a semicolon and there's no type being provided, then we just specify that. Here's an error. We expect semicolon and we parse the constant and assigned value. Now, the reason that we're not doing many complicated errors is maybe that's something for towards the end of the series. But for now, we're pretty much just going to panic when we encounter an error. I had someone message me on Discord asking how to handle errors, and I gave them a good walkthrough of it. And I'm happy to do that if you'd like. But the point of this series is not necessarily about error handling, though I could go down that route if people really badly want it. So let me know down in the description or on Discord. The point of the series is more about parsing, but the way we handle errors isn't too complicated. It's just a bit more work for each episode, so I'm trying to avoid that if I can. But basically, we would keep track of, inside the parser struct, instead of just these things, we'd keep track of the errors that we've encountered, and we'd be able to continuously build them. Now, let's quickly test our code and make sure it all works. And expected assignment, but received colon instead. Expected assignment, but received colon instead. Ah, nifty. So we have not fixed that. So let's see what we get here. So if the current token kind is colon, we do... Yeah, that looks good. We then parse that out. If the current token kind is not equal to a semicolon, we expect the assignment. We get the assigned value. Check. That looks really good. What am I missing here? I know I'm missing something. Always am. Let's look at this. So let's see if this parses first. Okay, so that parses. Lovely. Let's try to add let's just simplify this as well. Just 10 plus 5. And yeah, that parses. Cool. Let's try to do this as a number. Type led handler for token assignments. Type led. Oh, interesting. Interesting. So let's see what's going on here. So we have whether we're at a constant. We've checked that the colon is good. Yeah, if it's equal to colon, we expect the colon. If it's equal to the colon, we expect it. Expect the assignments. That looks good here. Okay, I think everything's fine in here, so it must be in our types go. Sorry, this one. So let's quickly just see what's going up. Binding power. Oh no. That's... Yes, so what we actually want to do is we don't want to have a type binding power. What do we do? Yeah, we do. But are we not using this somewhere in here? Type BP, type BP. Yeah, we are. And let's make sure parse type looks good. Type nud lu, type led lu, type lu, like so. That would explain it. Okay, type led handler expected for token assignments. Also again, type, Tyler, the amount of errors. Okay, sorry about that. That was sloppy. Okay, so we can look through here and we can see that what's happening is we encounter the colon. It then goes into the parse type, which by doing parse type, gosh, why is this the one that's open? When it does the parse type, right, we check the colon, we get the nud. Currently, there's nothing greater than this because the current token kind is going to be an assignment token, right? So it's going to pulp out of here with the explicit type. We then check the semicolon. Everything looks good. So let's just make sure I can't do, this should work. There we go, right? Body, bar, constant false, assigned value is nil, and it's a type of number, which means this should work. I should be able to say this is a number array now. And we get some good old-fashioned errors. Nice. Let's see what's going on with that. Let's see. So we go into the types go. And here we have parse array type. Oh, duh. Oh my gosh, tons of errors today. Sorry about that, guys. So currently, when we encounter this, we don't eat these tokens, right? So we need to expect these two tokens. So let's go in here, and all we do is we just do p.advance, p.expect, lexer.close bracket, like so. And there we go, right? So we say bar is false, has no value, but the explicit type is an array where the underlying is number, and this should obviously be recursive. So we should be able to add multiple like so, and we get an array of number. Perfect. Let's just make sure this doesn't work, right? This should not be allowed. Missing either right-hand side. Perfect. Let's make sure that this doesn't work for the constants. And we get the same thing. Cannot define a constant without providing a value. And let's just save this. And as we see, everything works. Again, we're not doing type checking. We don't do that at the parser level. We instead traverse the parser tree later. But this looks really good. So now we have types, which means we can now implement structs, function declarations, and a whole bunch of other good things with type syntax. Are we going to be writing a type checker? Not in this series, maybe in a future series. Like if we do any compilation, we'll be writing a type checker. But for now, we have the ability to add types. If you don't want them in your language, you basically just have to ignore all of the stuff we did here. And yeah, so if you found this video useful, please like, comment, subscribe, and feel free to reach out to me on my Discord server, which of course will be linked in the description down below. Until next time, happy coding.